in this lecture, we're going to be talking about circuit elements and network topology. From here on out, we're going to be delving into the circuit analysis, but first we need to lay some more foundations. So the contents are circuit elements, types of energy sources, which includes types of dependent sources, circuits versus networks, and some fundamental concepts in network topology, such as branches, loops, nodes, independent loops, and applications which relate to our course. And of course, we're going to have a quiz, which I highly recommend that you try your best in. So let's talk about circuit elements. To put it simply, they can be divided into active elements and passive elements. Active elements generate energy, whereas passive elements consume energy. Some examples of active elements are batteries, generators, and op-amps. And for passive elements, we have resistors, capacitors, and inductors, which are some of the most common examples. Now, keep in mind that in reality, active elements do actually consume some power because they're not ideal and they do have some parasitic resistance to them. But in electronics, something that we do commonly is that whatever characteristic a particular component has, we separate that into distinct elements where each element characterizes some aspect of the overall device. And we'll see examples of that as we progress through this lecture series. Now let's talk about types of energy sources. So an ideal independent source is one so it is an active element that provides a particular voltage or current independent of other sources. So for example, you could have an independent DC voltage source, and its symbol is shown here on the very left. Now, I personally prefer the circular symbol shown here in the middle with the polarities indicated, and this could represent either a DC voltage or an AC voltage. And typically, you will see that DC quantities are capitalized, whereas AC quantities are lowercase. So besides this independent voltage source, you could also have an independent current source, and the symbol is shown here with a circle and an arrow indicating the direction of the current, conventional current flow, and it could be DC or AC current as well. Now let's talk about ideal dependent sources. So an active element where the generated voltage or current is dependent on another quantity is called an ideal dependent source. So the symbol is usually a diamond, and you can see the type by the arrow or the polarity. It tells you if it's a voltage or current source. Now the types of dependent sources, so as you know, we have a voltage and current. These are the quantities that we care about the most in this lecture series and as electrical engineers. So naturally, this gives rise to 4 different combinations. So you could have a voltage-controlled voltage source, a voltage-controlled current source, a current-controlled voltage source, or a current-controlled current source. Now let's talk about circuits versus networks. A network is an interconnection of elements, very simply put. So in this case, you can see I have 3 elements and they're connected at a particular node. And a circuit is a network containing at least one closed path. So a circuit is a special case of a network. In this case, you can see a generic example of a few elements where they're connected in such a manner that there's at least one closed path. Since most people like to think about things visually, here's a simple representation of the difference between circuits and networks, and that is, circuits are a special case of networks. Now let's talk about some fundamental ideas in network topology and how they relate to circuit analysis. So a network consists of branches, nodes, and loops, and a branch is a single element in a network topology. So in this network topology, which happens to be a circuit, because it has at least one closed path, we can see that there are 3 different branches because there are 3 different elements present in the circuit. Now, a node is the point of connection between separate branches, and I've reshaped the circuit you see above here to one where you could more easily see the nodes. So the nodes, again, are the connections between each branch. So in this case, we have 3 different nodes. Now let's talk about loops. So a loop is a closed path in a circuit. And in the above example, you can see that we have one closed path and therefore one loop in the circuit. Let's now talk about a special case of loops, which are independent loops. And those are loops that contain at least one branch that is not a part of any other independent loops. So in the example you can see here, we have 3 resistors as well as 2 independent energy sources. And we have 1, 2, and 3 different loops that we could identify here. Now the question is, which ones are independent and which ones are just loops? So based on the definition, we can see here that only the first 2 loops are independent because they have at least one element which is not shared by other independent loops. So for the first one on the left, you can see that R1, for example, or the voltage source are contained within that loop and are not shared by other loops. Similarly, R3 is only used in the second loop and not in the first one. But R2 is shared between loops 1 and 2, and therefore the third loop, shown in green, is not an independent loop, only the first 2 are. Now let's move on to another important concept in network topology, and that is the fundamental theorem of network topology. Now this theorem relates number of branches, number of independent loops, and the number of nodes in a given network topology. Okay, so that's great, but how does this relate to circuit analysis? So as far as we're concerned, we can use the definition of a node to define what series elements should be like or how they should behave. So we can say that series elements must share a node exclusively. And what we mean by that is that you can't have multiple elements or branches joined at a certain node and still be in series. So in this case, you can imagine that if I have a third resistor connecting to this very node shown in blue, then the current will no longer be the same between those original 2 elements, because it will branch off into a third element or branch. So again, for elements to be in series, then we can say that the node should be shared between them exclusively and not by a third or a fourth or so on type of element. And in this case, for series elements, we know that they must have the same current flowing through them. Now, parallel elements, you could say that those are elements that share 2 nodes. So in the example below here, you can see a voltage source and 2 resistors. And for them to be in parallel, they must share 2 nodes to be considered parallel elements. And the special property of parallel elements is that they will have the same voltage across them. Okay, so now let's jump to the fun part. So we're going to take the quiz now, and before I let you start by pausing the video, let me just describe what's going on here. So in the first problem, we're asked to categorize the dependent sources below and what type they are. Are they a voltage controlled current source or whatnot? And you can refer back to the part of the video that was relevant to be able to find this part out. I'll give you a hint here, and that is that first jump right into which one is a dependent source to be able to deduce what type it is. Moving on to the second problem, we're asked to find the number of branches, loops, and nodes in the network below. And here I recommend you to find those values by inspection and also by the fundamental theorem of network topology. Okay, so now let's go on and solve the problems here. So for problem 1, we're asked to find the type of dependent source. And for part A, you can see that we have a input voltage of Vn with the given polarity, and the dependent source shown uses that quantity, that voltage quantity, to generate a current going downwards. So in this case, because we have voltage leading to a current output or a current quantity, then we will have a voltage controlled current source. For part B, we can see that we have a voltage source leading to a current I, which then leads to a dependent source having a value I over 2. So our dependent source is a current source, and it depends on another current in the circuit, and for that reason it is a current-controlled current source. For part C, we look immediately to the dependent source in a diamond shape, and we see that there's a polarity indicated, and that so we know it's a voltage source, and we also see that the value of it is 2 times V sub 0, and V sub 0 is a voltage quantity across this 10 ohm resistor here, and for those reasons we indicate that it is a voltage leading to a voltage or a voltage controlled voltage source. Lastly, for part D, we see an independent voltage source of 7 volts leading to a current I, and we see a dependent source that has a polarity indicated, which means it is a voltage source, but its value is 5 times I, which means that it is it depends on a current in the circuit. So it is a voltage controlled, it is a current controlled voltage source, and that should be indicated as a current leading to a voltage, not I to I. So it's I to V, a current leading to a voltage. So that is a current controlled voltage source. Okay, so let's move on to problem 2, and we're asked to find the number of branches, loops, and nodes in the network below. And before doing anything else, let's go ahead and just write the fundamental theorem of network topology, and that's a good practice to start writing what you know on an exam, for example. So let's start there. So we know that the number of branches are the number of independent loops plus n minus 1, which is the number of nodes. That's what n is. So let's first do this by inspection. So if we go ahead and count the number of branches we have, or elements, we can see that starting with the current source here, we have 1, 2, 3, 4, 5, 6. So you have 6 total branches or elements. And for the number of nodes here, which is a connection between each branch, we can see that we have 4 nodes, which are not necessarily where the blue dots are. The correction to that is that the 4 nodes should be between the 10-volt source and the 5-ohm resistor, between the 5-ohm and the 3-ohm, between the 3-ohm, the 2-ohm, and the 3-amp current source, and lastly, at the very bottom where one node connects the 2 resistors and the 2 energy sources. So then we have 3 independent loops, because each of them have at least one branch that is exclusive for that branch, so it's not shared by other branches. So we can go ahead and now solve for another variable here using the theorem of the fundamental theorem. So we can solve for branches. So we would have 2 variables that are known. So we would say 3 plus 4, so loops plus nodes minus 1, which is equal to 6. And we can check that that is indeed the number of branches. We could check for the number of nodes, given that we know the branches and loops. So we will rearrange the equation for n, and we would see that it is n is equal to b minus l plus 1. So plug the numbers in, and we would see that we have 6 minus 3 plus 1, and that is going to give us 4, which is the correct answer. And lastly, we could also check for the number of loops, given that we know n and b. So we would solve for L, and that is b minus n plus 1, which is 6 minus 4 plus 1, which gives us a number 3 as expected. Thank you for watching, and I'll see you in the next video.